Let's fabricate some experimental data and use the t-statistic and p-value to determine whether or not a given experimental result is a real effect or not. All right, let's get our hands dirty with some t-tests. We're going to actually fabricate some fake experimental data and run t-statistics and p-values on them and see how it works and how to compute it in Python. So let's start by fabricating some data here. Let's imagine that we're running an A/B test on a website, and we have randomly assigned our users into two groups, Group A and Group B. And Group A is going to be our test subjects, our treatment group, and Group B will be our control, basically the way the website used to be. So in this example, our treatment group is going to have a randomly distributed purchase behavior where they spend, on average, $25 per transaction with a standard deviation of 5 and 10,000 samples, whereas the way the website used to be had a mean of $26 per transaction with the same standard deviation and sample size. So we're basically looking at an experiment that had a negative result here. And all you have to do to figure out the t-statistic and the p-value is use this handy-dandy stats.ttestInd method from SciPy. It's just that simple. So what you do is you pass it in your treatment group and your control group, and out comes your t-statistic, which in this case is negative 13. The negative indicates that it is a negative change. This was a bad thing. And the p-value is very, very small. So that implies that there is an extremely low probability that this change is just a result of random chance. So remember, in order to declare significance, we need to see a high t-value, t-statistic, and a low p-value. And that's exactly what we're seeing here. We're seeing negative 13, which is a very high absolute value of the t-statistic, negative indicating that it's a bad thing, and an extremely low p-value telling us that there's virtually no chance that this is just a result of random variation. So if you saw these results in the real world, you would pull the plug on this experiment as soon as you could. Okay? So just as a sanity check, let's go ahead and change things so that there's actually no real difference between these two groups. So I'm going to change Group B, the control group in this case, to be the same as a treatment, where the mean is 25 with a standard deviation that is unchanged and its sample size is unchanged. So if we go ahead and run that, you're going to see that our t-test ends up being below 1 now. So, remember this is in terms of standard deviation, so that implies, well, there's probably not a real change there. And we also have a much higher p-value as well, over 30%. Now, these are still relatively high-ish numbers, so you can see that random variation can be kind of an insidious thing. This is why you need to decide ahead of time what is an acceptable limit for p-value here. You could look at this after the fact and say 30% odds that it's, that's not so bad. We can live with that, but no. I mean, in reality, in practice, you want to see p-values that are below 5%, ideally below 1%, and a value of 30% means it's actually not that strong of a result. So don't justify it after the fact. Go into your experiment knowing what your threshold is. Let's do some changes here. And, again, we're creating these sets under the same conditions. Let's see if we actually get a difference in behavior by increasing the sample size. So we're going to go from 10,000 to 100,000 samples. You can see here that actually the p-value got a little bit lower and the t-test a little bit larger, but it's still not enough to declare a real difference. So, you would expect that to... it's actually going in the direction you wouldn't expect it to go, right? Kind of interesting, but there's still high values. Again, it's just the effect of random variance, and it can have more of an effect than you realize, especially on a website when you're talking about order amounts. Let's actually go to 1 million. What does that do? Well, now we're back under 1 for the t-statistic, and our value's around 35%. So, we're seeing these kind of like fluctuate a little bit in either direction as we increase the sample size. This means that going from 10,000 samples to 100,000 to 1 million isn't going to change your result at the end of the day. And running experiments like this is a good way to get a good gut feel as to how long you might need to run an experiment for. How many samples does it actually take to get a significant result? And if you know something about the distribution of your data ahead of time, you can actually run these sorts of models. Now, just as a sanity check, if we were to actually compare the set to itself, this is called an AA test, and we'll talk about that more later, we should see a t-statistic of 0 and a p-value of 1.0 because there is, in fact, no difference whatsoever between these sets. Now, if you were to run that using real website data where you were looking at the same exact people and you saw a different value, that indicates there's a problem in the system itself that runs your testing, right? All right, so at the end of the day, like I said, it's all a judgment call. So go ahead and play with this. See what the effect of different standard deviations have on the initial data sets, or different differences in means, and kind of get a feel in different sample sizes. So I just want you to dive in, play around with these different data sets, and actually run them and see what the effect is on the t-statistic and the p-value. And hopefully that will give you a more gut feel of how to interpret these results. But again, the important thing to understand, you're looking for a large t-statistic and a small p-value. P-value is probably going to be what you want to communicate to the business. And remember, lower is better for p-value. You want to see that in the single digits, ideally below 1% before you declare victory. Okay? Let's talk about A/B tests some more in our next lecture. So there you have it. SciPy makes it really easy to compute t-statistics and p-values for a given set of data. So you can very easily compare the behavior between your control and treatment groups and measure what the probability is of that effect being real or just a result of random variation. So make sure you are focusing on those metrics and you are measuring the conversion metric that you care about when you're doing those comparisons.